Welcome back to another video. Our previous video introduced the lifetime utility problem that the individual or decision maker is trying to maximize. And we also introduced some of the basic assumptions that make this type of model tractable to solve. Today we'll introduce a two-period example that can help provide further intuition for what's happening. And we'll also introduce a fundamental concept of dynamic programming called the Bellman equation. These tools help reduce the recursive lifetime problem into a series of period-by-period decisions, where today's decision depends on what's happening today plus the expected future value of what's happening in the future. This expected continuation value or expected future value is what makes these models dynamic as opposed to static. So that's where the fundamental difference is between a static and a dynamic model. So let's start by thinking of our flow utility in the final period of life. And for simplicity, we're just going to assume there's two periods. There's cap t and there's cap t minus 1. And we do this so that we can understand intuitively how these problems are set up, which will give us a foundation for when we deal with more complicated examples. So just like in the last video and in static choice models, we have our big U is our little u plus epsilon. Little u is x times alpha. Now we're going to introduce something called the conditional value function, and we're going to roll back a period. So in period cap t minus 1, we're going to introduce this conditional value function that is indexed by I, j, and cap t minus 1. And this conditional value function is composed of the flow utility today plus the discounted expected future utility given today's choice. And you'll notice that the current period epsilon cap t minus 1 is not entering this equation, and we'll talk about why later on. And as before, beta is our discount factor. So now let's talk about something called the Bellman equation. The Bellman equation for a dynamic discrete choice model is given by this recursive formula. I have capital VIT on the left, and then I have an Emax of the current period utility plus the current period's epsilon plus the discounted capital V for the next period. So this is a nice way of depicting this dynamic problem because there's this recursive format to it. So as with the little v formulation that I just showed you, this big V formulation has the immediate payoff and the expected future payoffs that are discounted appropriately. We also call capital V the unconditional value function. And the reason why is because it's unconditional of the current period epsilon and the current period choice. Whereas the conditional value function is conditioning on the current period choice. That's why it's the conditional value function. And it's netting out the current period epsilon as well. So what is this expectation taken over in this Emax term? Well, it's taken over the future epsilons and the future x's. And the reason that we like to use this recursive formulation to form the Bellman equation is because it keeps the notation compact. So let's talk a little bit about this Emax term. We've talked about this before in a couple of previous videos. First, when we talked about an expected consumer surplus from the basic static logit mini-series. And then we also talked about it when we were thinking about nested logit as a multi-stage problem. And it came up as part of this inclusive value formulation. So the question that I have for you, the viewer, is what does this Emax formula look like if x is deterministic, given the prior x and the prior decision, and if the epsilons are type 1 extreme value? So go ahead and pause the video if you want to have a quiz. And once you've decided on the answer, you can check it right now. So the answer is that this Emax is the log of the sum of the exponentiated deterministic part of utility, or observable part of utility, plus Euler's constant. And what's the whole goal of having these dynamic discrete choice models? Well, we want to estimate the preference parameters so that we can then use those for policy experiments down the line. And so we want to estimate these alphas using maximum likelihood, like we would with the static logit model. And we indeed can, in this very simple example, if the x's are transitioning deterministically and if the Emax term has a closed form. So under this condition, we can write the conditional value function in period cap t is just going to be x times alpha j, y because cap t is the end of life, so there's no future periods after that. And then the value function in cap t minus 1, the conditional value function for choice j, is going to be the t minus 1 flow utility plus beta times the log of the sum of the exponentiated future utility plus beta times Euler's constant. And here, because we assumed that the x's are transitioning deterministically, that's keeping us from having any kind of expectation over x cap t. In a future video, we'll relax that assumption and we'll see how that changes things. So once we have this, we just treat the v's like we would the u's in a static model, and then we can just estimate with maximum likelihood. And in a future video of this mini-series, we'll cover that in more detail. So before we wrap up this video, I wanted to talk about when dynamics might not matter and just kind of have a thought experiment for what is it about the model that's generating this need for individuals to think about the future. So let's take our two-period model and let's think about normalizing the location of utility by taking the difference in two conditional value functions. So we have in cap t minus 1, we have the difference between Vij and Vij prime. So this is going to be the difference in the flow utilities plus the difference in the expected future flow utility in the final period, given whatever choice was made today. So the only difference between these is these blue terms. The only difference is that I chose j prime versus j in cap t minus 1. And so the point that I'm trying to make here is that if this future utility is the same, regardless of what I chose in the current period, then this is going to cancel and my v's are just going to become the u's that I had from the static model. So the main principle that I want you to understand is that in order for us to have v's that are different than the u's, in order for us to have dynamic behavior, we have to have it be the case that the choices are affecting the future states in some meaningful way. Now, what's the easiest way to satisfy this requirement? Well, the easiest way is to have a switching cost for different choices. So if I'm choosing, maybe I can choose to work or I can choose to stay at home. It's a labor supply problem. Maybe there's some kind of cost that I have to pay in terms of psychic cost or some kind of psychological burden if I change across those two sectors. So if I enter the labor force, then I'm going to have to have my schedule work around the time of my employer. I'm going to have to fire up my resume, start looking for jobs. There's some cost associated with that. And then likewise, if I exit the labor force, there might be some cost to adjusting to life as a home producer, etc. So the idea is just that these switching costs are going to make the decision makers consider the future when they're making their decision today. Because they don't want to just on a lark make this decision and then realize, oh, I didn't actually like that decision. I have to go back to where I was in the first place. So I hope that makes sense. This is the whole reason why we need to work backwards and think about the future when we're making our decision today, because we don't want to pay that switching cost in the future if we don't have to. So that's it for this simple two-period model. In the next video, we're going to generalize this to multiple time periods, any number of time periods, and also introduce states that transition stochastically instead of deterministically.